So far, we have talked about electromagnetic waves transporting energy, transporting momentum and all these things. What we want to focus on this, what happens when in this lecture is what happens when electromagnetic waves come at a boundary between two different medium. We all know they get reflected or transmitted. What exactly those coefficients are? We want to understand that, and this we should be able to derive from Maxwell's equations and related boundary conditions. So, first what I will do is motivate why reflection should take place at a boundary through mechanical waves, and then go over to electromagnetic waves. So, what we are going to focus in this lecture is reflection of EM waves at a boundary, and we are going to restrict ourselves, because we want to understand the phenomena, to waves that fall normal to a surface. But first, to understand that it is the boundary that gives rise to reflection, let us first understand that if there is a mechanical wave, for example, I could take a wave on a string. I could take a wave on a string that is going, and suppose we take two different strings, one of mass mu 1 per meter square, other one of a slightly different mass mu 2 per meter. Then what happens at this boundary? If there is a wave coming, let us say there is a wave that meets here, and then on the other side the same wave, let us say, goes like this. What happens? Now, at this point the displacement is y. Let us take this to be x equal to 0 without any loss of generality. The wave incident is y incident and wave transmitted is y transmitted. Let us say there is no reflection. Suppose there is no reflection, then what would happen? I know the displacement should look the same if I come from the two sides. So, at x equal to 0, I should have y I is equal to y t. What about one more equation? If I look at this point out here, this is a 0 mass point. You can imagine this to be a very small point mass with 0 mass, and therefore, force on a point at the boundary must be 0, otherwise it will move with an infinite acceleration. And what is force given as? Let us see that in the next slide. If I had this boundary where on the left hand side I have this displacement, on the right hand side I have another displacement, then at the boundary, if I look at from the left hand side, there is tension T in the string. Recall that I am taking a very small amplitude. So, T remains the same, and therefore, at this point feels a force of T at this angle, which is at an angle theta. This provides the horizontal component T cosine of theta. Let us call it theta 1, because I am coming from the left side, and vertical component T sine theta 1. On the right hand side, I have same tension, but it making angle theta 2. So, the horizontal force is going to be T cosine theta 2, and the vertical force is going to be T sine theta 2. For a small angle approximation or a small amplitude, I can take cosine theta 1 and cosine theta 2 to be 1, and therefore, the horizontal components cancel and they give you 0, because the component for the blue one is towards the right and component for the red one is towards the left. However, the vertical components, since I am taking T cosine theta sin theta 2 to be going up. So, it will be t theta 2 minus theta 1. Theta 1 is roughly same as tan theta 1, which is same as d y incident by d x. Similarly, theta 2 is tangent theta 2, which is d y transmitted over d x. And therefore, the net force is going to be T d y transmitted over d x minus d y incident over d x. And from the wave equation, I can write this, both the waves are traveling to the right. Therefore, T d y t over d t 1 over v 2, where v 2 is the velocity in the right string, plus 1 over v 1 d y t over d t, d y I over d t, and this should be 0. So, the two equations that I have are this string from the left hand side, the string on the right hand side. I have y incident is equal to y transmitted, and I have minus 1 over v 2 d y transmitted over d t plus 1 over v 1 d y incident over d t is equal to 0. Since y incident is y t, all the time I have d y incident d t as d y t over d t, because they remain in phase. This condition is satisfied for all the times, and therefore, I have minus 1 over v 2 plus 1 over v 1 d y I d t is equal to 0. This means either this slope is 0, that means there is no velocity for the midpoint, the point at the connecting point, or velocities are the same. If the velocities are the same, two mediums are the same, and therefore, the entire wave transmits, but this certainly cannot be 0. How do I then satisfy the equations? Right? Either I get that d y I by d t is 0, which is not possible, or velocities are the same. To satisfy all the equations all the time, therefore, I have to then take that there exists a y reflected also. So, whenever there is a boundary, so that the speeds at the two sides of that boundary are different, there has to be a reflected wave also. Otherwise, I run into problems of satisfying these equations, which are true nature given equations. So, now what we are going to say is that given this string of a different mass on this side and different mass on the right side, there is going to be a incident wave, a reflected wave with y r displacement, y incident displacement, and a transmitted wave with y t displacement. Again, since at the boundary we should have the displacement the same all the time, I should have y incident plus y reflected is equal to y transmitted. That is equation number 1. I should also have the net force 0. Now, the net displacement on the left hand side is y I plus y r, and its vertical component is going to be theta again, which is d by dx of this times the tension. That is the net force on the left hand side. From the right hand side, I am going to have, this is with a minus sign, plus from the right hand side, I am going to have t dy transmitted over dx is equal to 0. That is my equation 2. Let us convert them into the time equation. So, I am going to have t, I can drop because this is 0 on the right hand side. I am going to have d y I over dx with a minus sign minus partial y r over partial x is equal to minus partial y transmitted over partial x. All this can be made to be plus. Incident wave is coming from left to right, and therefore, this is minus 1 over v 1 d y I by d t. The reflected ray goes to the left, therefore, this is plus 1 over v 1 dy r over dt, and this should be equal to minus 1 over V 2 dy transmitted over dt. Again, the displacements are same all the time, and therefore, I can take the time derivative out and I can write minus y incident over V 1 plus 1 over V 1 y reflected is equal to y transmitted over V 2 with a minus sign, or minus V 2 y incident plus V 2 y reflected is equal to minus V 1 y transmitted. This is my equation 2. I solve the two equations and I will get results for y transmitted and y reflected in terms of y incident. Let us do that. So, let me rewrite the equations on the next slide. I have y incident plus y reflected is equal to y transmitted, equation 1, minus V 2 y incident plus V 2 y reflected is equal to minus V 1 y transmitted, equation 2. Multiply equation 1 by V 1 and add to equation 2. I get V 1 minus V 2 y incident plus V 1 plus V 2 y reflected is equal to 0, and this gives me y reflected is equal to V 2 minus V 1 over V 2 plus V 1 y incident. So, we have gotten what y reflected is. Again do a similar manipulation and you are going to get y transmitted is equal to 2 V 2 divided by V 2 plus V 1 y incident. Let us check the boundary conditions quickly. If I take y I plus y r, which is equal to V 2 minus V 1 over V 2 plus V 1 plus 1 y I, this indeed gives me 2 V 2 over V 2 plus V 1, which is my answer here. Notice in this that if V 2 is smaller than V 1, y reflected is an opposite sign to y I. That means, if I have a heavier string on the right hand side, which makes V 2 smaller, I am going to have a phase change for the reflected wave. Now, this is the answer that we get for a wave on a string. You can also show with these amplitudes that the energy coming in is equal to the energy reflected plus energy transmitted, which is required by energy conservation. Exactly similar equations are now going to be obtained for electromagnetic waves. For electromagnetic waves, the boundary conditions are in terms of electric and magnetic field, right, and those boundary conditions are going to give us what amplitude of the incoming electric field is going to, what fraction of the incoming electric field is going to be reflected, what fraction is going to be transmitted. That we will do in the next lecture.